Can somebody wave at Nicole on on Zoom and to signal that you can hear me? Okay, that's the sign we were hoping for, right? Okay, so welcome. Today our speaker is Seth Kellogg. Some of you might, if you might have seen Seth talk, was it 5 years ago last time? Seth is a graduate from Alfred University with a BA in geology, and it was followed by a master's in hydrogeology from Indiana University. After that, she worked for a number of engineering firms over the years, but for at least 6 years, she's worked with Geosyntec and now is a senior principal there. I thought it'd be worth mentioning she's volunteered for many years in the National Groundwater Association, a professional organization, and she's holding positions of leadership now there. And she's also a trustee of the Hunterdon Land Trust in New Jersey, so that's great. Seth has long worked on pollution issues with mercury, with VOCs, volatile organic compounds. But for a number of years now, she's become a leader in addressing PFAS's contamination. So I'll let you describe what PFAS. We hear a lot about PFAS in the news these days. This summer, there's some big news that came out with agriculture and PFAS, and so that kind of stuff is re-emerging more and more in the media, and it's an important topic. So with that, we'll let you take it up from here. Thank you.
Good. All right. All right. Ooh. You never, ever get away without a technical issue. It just doesn't happen. Well, thanks everybody for having me today. My name is Seth Kellogg. As Fred pointed out, when I was here, my maiden name was Richardson, and I went by D because my given name is Dorothea. I found the hard way that, or I guess the easy way, that that geology was a very male-dominated field. Do you want me to try talk? Can you? Okay. I will do my best because I hate standing behind a podium, but I will do my best. But so I again started off in environmental policy. I realized that I liked science better than policy, and went back to graduate school, and then had a 20-year career where I was really focused on chlorinated solvents, finding and cleaning up chlorinated solvents, and then PFAS came along, and you know, it was a new thing. We're still trying to figure out how to deal with them. And it's been a really exciting time in my career for the last 10 years. And we have a lot more to learn. And so I think the opportunity to be curious and the opportunity to learn new things has been the best part of my career as an environmental professional. So this is where every time I look at these types of slides, I appreciate Dr. Bentz and his patience. But basically, per and polyfluoroalkyl substances is what PFAS stands for. Sometimes you'll also see it, the acronym with an extra S is PFASes. But basically what per means is that every carbon on the chain is bonded to a fluorine. So it's a 1-to-1 ratio. When you're talking about polyfluorinated substances, you have other things bonded to the carbon besides the fluorines. What that makes is they make weaknesses in those molecules. So when you hear about forever chemicals, those are the perfluoroalkyl substances. The polyfluoroalkyl substances are sometimes referred to as precursors, or again, they can break down into those perfluoroalkyl substances. What's also interesting about these molecules is that they contain a head and a tail. And generally, the head and the tail like to be in different states. So the head wants to be in the water or the fuel, and the tail wants to be in the air. Or the head wants to be bounded to a piece of a solid or a sediment, and the tail wants to be in the water or the air. So you tend to find these chemicals at interfaces, and that's why they are so useful in a lot of industrial and commercial processes. Some unique properties that they do have the carbon-fluorine bond is the strongest and most stable bond that exists in nature. It's almost impossible to break naturally. They're very resistant to heat, water, grease, and they reduce friction. They can both be hydrophobic and lipophobic, but at the same time be hydrophilic and lipophilic. So again, they like these interfaces. And a lot of these properties are very desirable additions to industrial, chemical, and consumer products. And we'll talk about that a bit more. So because of this, we talk about PFAS as a group and PFAS as, when you see it in the news, when you see it on John Oliver or The Daily Show, it shows, PFAS is that headline, but they're not all the same. Right now, EPA is regulating 6 PFAS compounds, but they're gathering information on 12,000 of them. So you can't always assume that a PFAS is a PFAS is a PFAS, and they're not always all equally as bad for you. So they can come in the monomer type, which are smaller molecules with no repeating units. These do tend to be more available. They can also be polymers, which are bigger molecules with repeating sequences, and those tend to be less bioavailable or less toxic. And then there's Zwitter ions and oligomers and all these other great chemistry terms that I haven't heard in 30 years until I got to PFAS. And the ITRC, or there are some other great references online that if you really want to go into a lot of the deep parts of PFAS chemistry, that they'll teach that stuff to you. I will also say that the length of the carbon chain and the functional group really does regulate the behavior of the individual PFAS in the environment. So longer chains with sulfonates, so anything with an S on the end, so you hear PFOS as an individual compound, those tend to be less soluble. They will stick to soils or sediments, and they are more likely to bioaccumulate in animals, as opposed to shorter chains and carboxylates. Carboxylates is anything that ends in an A, tend to be more soluble, so you'll find them more in the water. They will less stick to solids or sediments, and they tend to be more bioaccumulative in plants. So when we're thinking about this as environmental professionals, understanding what the suite of PFAS that you're dealing with is really important to understanding what the target would be or what the receptor would be, who could be impacted, as well as what your remediation strategies would be. And I love a good Venn diagram. So I just want to highlight the icon on the right. Basically, like, PFAS has all of the properties of all the most difficult chemical families that we've ever had to deal with as environmental professionals. So they are complex mixtures. They're highly mobile, or can be highly mobile in groundwater, and they're incredibly stable. So they're the only very mobile class of chemicals that will transfer from surface water to groundwater, back to surface water, into the air. And we'll talk a little bit about the PFAS cycle and where we find PFAS. And a lot of that is because they just don't break down. So every time we put more into the environment, it just is more in the environment. It's unlike petroleum or chlorinated solvents, there are no natural processes to break these down. So just to highlight this a little bit more, this is some of the more recent research that's coming out of University of Arizona from Brousseau and Gao. And this is the nerdy stuff that I really enjoy. But because of the fact that we're looking for these substances at incredibly low concentrations, I mean, some of the EPA standards are set at a place where you're looking for 1 grain of salt in an Olympic-sized swimming pool, and you're trying to clean that up. So because of that, a lot of these factors that we don't consider when we're looking at petroleum products or chlorinated solvents in water really start to matter when we are looking to clean up PFAS compounds. So the actual interactions between a molecule of PFAS and a grain in an aquifer can matter as to whether you can get that molecule out or not. We're seeing the same things as far as, the leaf litter decomposition and the soil pH. All of these things really have a strong impact on whether we can remediate down to the levels that these compounds are currently regulated at. So to spend a little bit more time on the chemistry, again, the big family is called PFAS. That's broken into the per and the poly. And the ones that we really care about, I don't know if anybody can see, but the ones we really care about are what's called these perfluoroalkyl acids, or PFAAs. And those are broken down into the PFSAs and the PFCAs. But as far as, human health and as far as regulating these compounds, this is the part of the world that we're generally in. So how did we get here? So essentially, PTFE, which is Teflon, was discovered in the 1930s. It was incredibly useful during the Manhattan Project. Nuclear weapons would not be available or possible without it. And throughout the 1940s, we started to realize how useful these things are. And again, they resist heat, they resist grease, they reduce friction, and they reduce, they resist water. So starting in the 1950s, we see them showing up in stain-resistant products. These are your Scotch guards, a lot of carpet treatments. In the 1960s, we developed aqueous film-forming foams, which is a firefighting product, also incredibly effective. Basically what happens is the head of the PFAS dissolves into a petroleum product and the tail sticks out and it creates a foam that prevents oxygen from accessing the liquid fuel, which again is incredibly effective at putting out a fire, especially when you're thinking about these in a military setting or around munitions. We also start seeing in the 1960s PFAS getting added to food packaging. Again, remember, it resists grease, it resists water. These are great things to line microwave popcorn bags with or granola bar bags with. In the 1970s, we start seeing it show up in waterproof coatings. Like, I love my waterproof boots and I love my Gore-Tex jacket. Like this is why it started, these are again, incredibly useful. In the 1990s, the other place we find a lot of these is in chromium plating. So it actually was used as a dust suppressant. So once we figured out how bad chromium was for people that were working in chromium plating, they started adding PFAS to the chromium plating solutions to reduce the surface tension to prevent volatilization of the chromium. So in the 1990s, we actually thought that PFAS was something that was going to be good, that was going to reduce concerns and issues from other potential contaminants. So starting in the 1970s, we started noticing that people that were working with and manufacturing PFAS compounds were having high levels of PFAS show up in their blood serums. And then again, in the 1980s, there was a site in Parkersburg, West Virginia, where next to a facility that was manufacturing PFOA, in particular, Teflon in particular, there was a farm, and the cows started dying at the farm that were drinking the water that was coming out of this plant. And if anyone's ever seen either The Devil We Know on Netflix, or I think it's Dark Waters with Mark Ruffalo, like that is the site, that's the story of that site. I have a feeling like if you realize that story unfolded over the course of 20 years instead of an hour and a half, it probably was less dramatic in real time than it was, but it was still a cool movie. So basically what happened in the 2000s is the people that had sued the company that sued DuPont decided that they were going to take the settlement money from DuPont, and instead of dividing it among the families, they funded what they called the C8 study, which demonstrated the human toxicity, particularly of PFOA. And they had 80,000 people that participated in that study. And we'll talk more about that study later. And that essentially, forced several companies out of manufacturing PFOA and PFOS in the United States. It led to this voluntary stewardship program that EPA has monitored within the United States. But really where we've gotten is we're still getting, PFOA and PFOS and a lot of these toxic PFAS compounds coming into the country either in raw materials or finished or waste materials, it is still manufactured around the world. And the figure on the right-hand side is essentially where we started with PFAS and regulations and kind of where we are now. So starting in 1990, we were thinking that we were like 1,000 parts per trillion. So 1 part per billion number was going to be where this is toxic. And we've now gotten down to EPA's standard is 4 parts per trillion. So the more we've learned about these compounds, the lower the concentrations have got, the lower the safe concentrations have gotten. So what have we used this stuff for? So we have been incredibly effective at spreading this all throughout these compounds all throughout our environments. We use them in oil and gas. Again, they reduce frictions. So a lot of drilling fluids or fracking fluids had PFAS in them. Your cell phone wouldn't work if you didn't have a PFAS-based coating for your touchscreen. A lot of buildings for LEED certification require these really high efficiency coatings on windows. Paints, dyes, stains, medical equipment. At this point, we've kind of figured out replacement chemistries for water resistance for PFAS. We haven't figured out replacement chemistries for coatings for bloodborne or grease-based products. So you can't basically have a good surgical gown or a stent or a lot of medical equipment without currently using PFAS compounds. We're also seeing a lot of PFAS that show up in personal consumer products and cosmetics, or personal care products and cosmetics. There was a study that came out in June of this year that showed that 4% of the waste or 4% of the PFAS that's going into wastewater treatment plants is actually from things like shampoos and cosmetics and facial cleansers and all of those things. And then I do want to highlight, we can't create semiconductors without PFAS. So, all of the states that are both regulating PFAS as a class right now and want to promote semiconductor production in their state are really struggling with how to find that balance. So again, just to go over where you can find it in your house, dental floss, nail polish, electronics, guitar strings. I think one that was particularly heartbreaking to me was it's in ski wax. Some of the highest concentrations they've ever been found were actually in start gates in Switzerland. And there was a big, the most recent Winter Olympics, there was a big controversy that they banned PFAS-based ski waxes, and one of the European countries attempted to smuggle it in because it really does have that much of a performance advantage. But again, when you're thinking about spreading this stuff across everywhere, the way we've been able to do this, when you think about septic systems, when you think about wastewater treatment plants, when you think about landfills, all of these become a circular economy when it comes to PFAS because they don't break down. So we're not putting them someplace and they don't stay there. They are transmitted to other parts of the environment. And I guess on the last thing I wanted to highlight is that we're expanding definitions of PFAS. So in 2014, when I started working in this field, we had 6 PFAS, 6 perfluoroalkyl substances that we were worried about. Currently, EPA is collecting information on 12,000 compounds, and the definitions change. Like the state of Maine considers anything that has more than 1 fully fluorinated carbon as a PFAS and are regulating it. So we need to think about the fact that this incorporates pharmaceuticals now. So Prozac and Lipitor are both technically PFAS under some of these definitions. Also, refrigerants are coming up as PFAS under some of these definitions. So Freon in particular. So as we expand the definitions, as we start looking at more and more of these things, we're running into intersections of what is necessary for modern life and what is necessary for the economy versus how much information do we have as to how toxic that may or may not be. Because we have a really good body of knowledge around a handful of PFAS. But now when we're starting to talk about 12,000 PFAS compounds, we know very little about most of them from a human toxicology perspective. So just to sort of, close this loop to be a little punny on the PFAS cycle, essentially what we are very successfully doing is using these products in industrial and commercial uses, as well as personal care products. It goes into landfills, it goes into, wastewater treatment plants. In wastewater treatment plants, there's no treatment for PFAS. It usually ends up either in the river or in biosolids. And then those biosolids tend to be applied to farm fields as beneficial use. So remember how we talked about that there are some PFAS that have more affinity to animals, and there's some that have more affinity to plants. Think about that in an agricultural setting. If you are applying these PFAS, you're going to get preferential transfer through the food chain depending on what the food source is for each of those processes. I guess I do want to, we're going to talk about regulations next, but I do want to highlight the drinking water piece of this. So the general understanding is that only about 20% of human exposure comes from drinking water. And if you're talking about, 4 parts per trillion is the safe exposure concentration for drinking water, that assumes that you're getting 80% of your PFAS from someplace else. So as we're talking through what those regulations look like, just keep that in mind. So where is this stuff? So we are in the process of having EPA collect information from water sources across the United States. But USGS has sort of done this presumptive calculation, which is the map on the right-hand side. And they are estimating, based on the information that EPA has now, EPA is gathering additional information, that we've got about 57,000 sites in the United States that are going to be impacted by PFAS. And these are, airports, they're military facilities, wastewater treatment plants, industrial facilities. And, this is, again, something that we're going to have to manage as a society, because the idea of going out and cleaning all of these things up to these really minuscule levels, the amount of money that would take is prohibitive at this point. So figuring out different strategies, figuring out different approaches for these regulations is going to be necessary. So going back to talking about that C8 study that was funded as part of the Parkersburg, West Virginia, essentially what that study, the epidemiological study of 80,000 people, it started linking high cholesterol, testicular and kidney cancer, ulcerative colitis, thyroid disease, pregnancy-induced hypertension, and reduced antibody responses to PFAS, PFOA, PFOS in particular. I do want to point out that this is the first class of chemicals that we've actually seen the cancers be more impactful to men than to women. So a lot of chemicals have affinities to adipose tissue or fat tissue, which tends to impact females more. PFAS tend to have affinity for proteins. So men with higher proteins, obviously organs like kidneys, testes that have higher amounts of protein, tend to be the target organs for these compounds. And I guess we can talk about these excess cancer rates, but when we're setting regulations in the United States, when we're setting them based on cancer risk, the excess cancer risk is a 1 in a million cancer risk. So if you think about the fact that there are 330 million people in the United States, basically what we're saying is that compound is useful enough for us as a society that we're okay with 330 people getting cancer, to use these chemicals. That's the thinking behind a lot of the way these risk calculations are set out. So if you think about this excess cancer rate, being somewhere between 2 and 5%, or 2 and 5 times, obviously the PFAS chemicals had a significant impact. Yes, I had a timer set on that one. So I guess just to go over this, to sort of hammer home the whole PFAS cycle as well as the environmental exposures, we are seeing PFAS show up in places that we would not expect them to show up. So they're showing up in polar bears, they're showing up in fish. We're seeing them in the deep oceans, as well as metropolitan areas, wastewater treatment plants, all those sorts of things. So we've gotten to the point where we have effectively spread all of PFAS pretty much everywhere. And I think I was at a conference earlier this year, and there was a statistic that stuck out to me. One of the environmental regulators said that it costs $10 to purchase a pound of PFAS, and it costs $10 million to take it back out of the environment once it's gotten out there. So that was a little terrifying. So how are we regulating all this stuff? So the states actually kind of got out front. EPA's, the federal government's process for creating regulations is very slow and deliberate. So many of these states decided to get out in front and regulate a lot of these PFAS compounds, primarily so that they could force companies to do cleanups. But what it left us with was this really interesting patchwork of regulations and numbers. So you can see on this, these are the state numbers that we've got now. Ironically, Texas was one of the very first states to regulate PFAS, but their regulation is at 560 parts per trillion. So if you're a company and you have a facility in Texas and you have a facility in, say, Massachusetts, where Massachusetts has their number set to 20 parts per trillion for a sum of 5 PFAS, how do you communicate to your employees? How do you communicate to the communities that, well, what Texas says is safe is different, and the regulations you're following in Texas are different than the regulations you're following in Massachusetts? And this has opened companies up to a lot of litigation and a lot of challenges communicating with their communities. So I think I don't think there was another point I wanted to make on. Oh, I guess the other point I did want to make on this one is that, you can see all the gray states through here that have no PFAS regulations at all. And again, the companies that we work with really struggle with this because there's no reason that they have to be proactive. They don't have to limit their emissions of PFAS. However, they're well aware that this is coming, and they're trying to balance the risk with their business costs of how they're going to approach this moving forward. The other thing the states are doing is they're proposing or enacting consumer product laws. So California, Maine, and Minnesota have really led the charge on this. But basically, they're telling companies that they have to fully get PFAS out of food packaging and carpeting and juvenile products and personal care products, cosmetics. I always joke that, anything that floats above your wrinkles probably has PFAS in it because, it resists the oils, and that's, that's again a useful property that it has. So what we're seeing is more and more the states are forcing both cleanups on the cleanup side, as well as saying, okay, we're done putting more of this into the environment, and we really need to figure out how to stop making the problem worse. There are also, we haven't talked a lot about aqueous film-forming foams, but you will, if you Google PFAS, AFFF is something that definitely comes up a lot. about 5% of the PFAS contamination or 5% of PFAS that were produced were used in AFFF. And so this is essentially, it's very concentrated. These formulations have millions of parts per trillion of PFAS in them. And for the last 50 years, essentially, anytime there's been a car fire, the local fire department deploys this stuff. Anytime that there's a fire training at an airport, this stuff was deployed. A lot of military bases have a big challenges with the AFFF usage. So this is kind of the low-hanging fruit of how to regulate PFAS. And so a lot of states have really gotten ahead of trying to make sure that AFFF isn't used in their facilities anymore. However, the fluorine-free replacements haven't totally caught up with this. So if you're a petroleum facility, say you have bulk storage petroleum facility where you've got these giant tanks, there are probably options for you to switch away from these PFAS-based products. However, if you're a chemical plant and you have fluorinated solvents or you have other alcohol-resistant type of chemicals, the fluorine-free replacements just aren't there yet. And so it is still safer from a life safety perspective to use the AFFF than it would be to switch to water or other less effective products. So this is a struggle that we're having to come up with replacement uses. But in all of these states, the states are banning manufacture, sale, distribution, or use of AFFFs. And again, this is causing a lot of companies to figure out how they're going to move away from these different categories. So I will go through this as quickly. I'm sorry that this is alphabet soup, but this is the federal regulatory framework, and it is alphabet soup because that's what it is. So basically, the federal framework is supposed to be a cradle to grave framework. So we sort of start with RCRA and EPRA. So RCRA is the Resource Conservation. Well, we start with TSCA. So TSCA is the Toxic Substances Control Act, which you're basically supposed to ask EPA or prove to EPA that your stuff is safe before you use it. And then you're regulated under RCRA, which is the Resource Conservation and Recovery Act, which basically says you're responsible for it from the time you make it to the time it's disposed of appropriately. And then EPRA is the Emergency Planning and Community Right to Know Act, and that is you have to tell everybody where the stuff is. So this is where TRI reporting and your local fire departments make sure that they understand where all this stuff is. And then you can go through your Clean Air Act and your Clean Water Act, and then the Comprehensive Environmental Response Compensation and Liability Act, which is typically known as Superfund. And those are really all to help people clean stuff up when it's where they don't want it. But basically, as EPA has rolled through this, we've started with CERCLA. So the first place that they've gone to regulate these are under the Safe Drinking Water Act, and then they've categorized 2 PFAS as hazardous substances under CERCLA. So right now what they have the ability to do is they have the ability to clean it up after it's been spilled, and they have the ability to treat a point source for at a drinking water source. But they have not gotten to a point where PFAS is engaged in the entire cradle to grave structure of federal regulations. So just to point out that these were the MCLs, or the maximum contaminant levels, that were promulgated. Essentially, EPA comes up with what an MCLG or an MCL goal. So for example, like lead, the MCL goal is 0 because we know that lead is terrible. In this case, PFOA and PFOS, the goal would be 0, but they know we can only measure down to 4 parts per trillion with the laboratory methods. So that's basically where they've set it. They also have this interesting hazard index scheme, which essentially says you have to add up these 4 substances and divide them by each individual standard. And then if you get 1 or below, you're within compliance, and if you get 1 or above, you are out of compliance. And that is a new way to regulate things under the Safe Drinking Water Act. We haven't done this before, so we're expecting there to be a number of challenges, as far as legal challenges for challenging the validity of the science behind a lot of these goals and standards. I also wanted to highlight, part of EPA's setting of these standards is that they have to evaluate the costs and benefits. And essentially what they've done is they've quantified some parts of this. So basically they're saying it's going to be $1.5 billion a year to monitor these materials, to do the necessary upgrades for the wastewater treatment plants. However, they haven't quantified the costs to comply with the hazard index or other MCLs that they've set. So it is a challenge. And again, I think this is a place that these regulations are going to be challenged, is that the true costs or the quantification of these costs are really not well known. And the potential impacts are not as well quantified. So I don't want to imply in any way that the science behind these standards isn't sound. It absolutely is, and we've got 30 years of toxicological data to support what these numbers are. But the way EPA went through the process and the way they quantified different things is going to make it difficult for them to defend this process in court. So I just have, this is my last topic as we, to wrap this up, just to give you a way of thinking about PFAS. So there have been several studies that have quantified what they call anthropogenic background. So normally as geologists, we think of like background arsenic is what was in the rocks when you got there, or background radiation is what was in the environment. Because we have used these chemicals for as long as we have, about 70 years, we have essentially created an anthropogenic mush. So we created it, but there is no specific source and there is no specific individual or company to go after to have this stuff cleaned up. And so as we're thinking about what we're going to ask from a cleanup and remediation standpoint, we need to think about what's reasonable, what's possible, what's feasible. And to do that, we really need to keep this anthropogenic, mush concept or anthropogenic background concept in mind. So we see site after site after site where we get results from monitoring wells, say between 20 and 80 parts per trillion of PFAS, but there's no pattern, there's no distribution, there's no, all the things that we normally look at from an environmental perspective, we can't quantify that as a plume, and we can't quantify a source and a receiver. So it is making it challenging to talk to regulators who are like, my number's 4. And you're like, okay, but like there's nothing I can do to get there. So again, just going back to this PFAS cycle concept, the reason we need to consider this is because we have been effectively moving PFAS through our environment. We've even seen sites where the water distribution system is a problem because all pipes leak, and the sewer system is a problem. But if you send water out from your water treatment plant that's 100 parts per trillion and it leaks a little bit between here and all the houses that you get to, or the sewage that leaves a house, it leaks a little bit before it gets to the wastewater treatment plant, all of that is impacting the soil and the groundwater, and again, spreading these chemicals throughout the environment. So I think that's where I was going to wrap it up for today. So if anyone has any questions or thoughts or comments. Yep. Yep. I would say it's different for different states. So in the coasts obviously are more politically inclined towards environmental regulation. But, you know, I was at a meeting and I sat next to the head of Kansas Department of Environmental Protection. And she basically said, she's like, I'd love to regulate this stuff. We have all these military bases. I know my people are impacted, but the laws in Kansas specifically say that if the feds don't regulate, Kansas can't. So it really is, it depends on where you are. It depends on what the states are allowed to do. And it depends on the resources that those states have. So this is where you're getting to the nerdy toxicology stuff, and I'm a hydrogeologist, so I will speak to it as well as I can. But a lot of these things, you know, the idea, the epidemiological study is really valuable because it takes place in humans. A lot of the toxicology that happens around PFAS is done in imperfect analogs. So particularly like rats, you know, lab rats. To get a blood concentration equal to a human blood concentration, because rats don't bioaccumulate PFAS, they have to give them such a high dose that it confounds a lot of the results. So you don't really know whether the dosing is the issue or whether the blood concentration is the issue. So I can certainly put you in touch with people that I work with that have a lot more of that toxicology background. I'm not aware of any specific analogs that have been, you know, done as far as the human body goes, but I can certainly pass you on to folks that would have a better answer.
Hold on. I think it's working now, so people can hear you.
So until the federal regulations catch up, do you see kind of a race to the bottom for some states like, I don't know, Idaho and Indiana? They come over here, industry, we don't have any regulations that will get in the way. Like, do you see some of that?
I guess what I see more of is you know, companies taking advantage of the differences in regulation. So I don't see like the state of Louisiana saying, hey, come, you know, dump all your PFAS in our backyard. Like, they're not looking for that. But I do see companies shifting operations to places where there are more flexible environmental laws. And you know, the gray states, it's not just PFAS. Like, in general, the environmental laws are either more generous or just not as enforced. You know, a lot of even the federal standards are the states are the ones that enforce them. The states are the ones that you know, choose how to implement these programs, and you know, that varies state to state.
Hold on a sec.
The article was just recently talking about the wastewater and using sludge applications on farms and how toxic that is. And that's when I was like, oh, microwave popcorn and other things. But I have two questions and they're kind of related. So as a consumer, number one, are they labeled and identifiable in packaging? And so I think that kind of leads me to number two. If you wanted to kind of reduce your own consumption of an exposure to PFAS, probably as individuals, we can't regulate our drinking water so much, but what would you recommend are sort of the biggies that would make the biggest difference for people that wanted to limit their exposure?
That's a really good question. So, you know, California has done a really good job. There are Prop 65 labels on a lot of things, specifically for PFOA and PFOS. So you can always look for the Prop 65 labeling. The FDA has is requiring a transition away from a number of these PFAS in their food packaging. So again, it's sort of like the drinking water standards, those are going to be in place in 2029. So EPA's come out and said 4 parts per trillion is the standard, but every water company has 5 years to get into that. I guess I'm going to answer you in 2 different ways. One, I get in my car every day. And there's a 1 in 10,000 chance that I'm going to die in my car every time I get in that car. So, like when you're thinking about the relative risk of everything, like consider where PFAS really falls in that relative risk of all the risky things that we do. I personally have tried to move away from anything that has stain guards on it, particularly carpets. Particularly for small children. We also, we filter our water. We try to use purchase food that has less packaging associated or is less ultra processed. But those are all luxuries that I have the ability to make those choices, and those not everyone has those same sorts of things.
Hi. I just had a question. I know you said that these are basically like almost impossible to break down like naturally. Is there like a process they've discovered that they are able to break it down like in any sense? And then if so, like would they ever be able to implement that with like the septic treatment system or like maybe like a landfill system? Like is there any process that maybe could be explored there with that?
Yeah, and as I was putting this together, I was like, there's no way I'm going to get to treatment. I'm sorry, Norman. I'm happy to come back and give a forum another time on that. So everything that breaks down PFAS or destroys PFAS is a really energy-intensive process. So most of the ways we're cleaning these things up are sorbing them to carbon, we're sorbing them to different ion exchange resins, or filtering them out in using reverse osmosis. I think the next phase of this is there are technologies that will concentrate the PFAS, because if you're trying to treat water that's at a 10 parts per trillion with this really high energy treatment system, like it becomes prohibitively expensive. So can we concentrate the PFAS and then use those really high energy like plasma or thermal like incineration or the thermal destruction types of technologies. But at this point, we've come up with in situ or in situ chemical ways to treat almost everything else. They're like ISCO and ERD and like biology, but there are no biological options or in situ options for this stuff. So it's just very expensive to treat at this point. I think even EPA's recommendation right now is deep well injection, which to me seems like a terrible idea. But basically they say, take it to Oklahoma and inject it 2,500 feet underground. So yeah, we'll see how that goes.
Or Kansas.
Or Kansas, yeah.
Well, thank you. If you have any more questions, you want to ask.